overview of hypothesis testing. We'll learn how to test if the collected sample data actually provides compelling evidence to warrant the acceptance of a manufacturer's hypothesis about a product. That's basically what we're going to be doing from this point forward in the course. For example, if the makers of Gestamax claim that the vitamin will increase pregnancy length, we'll learn how to analyze the sample data to determine if the maker's claim can be justified. To better understand the basis of hypothesis testing, we'll compare it to the judicial system. Okay, so once an individual is accused of committing a crime, a trial is conducted to determine if there is evidence to convict the individual. The defendant makes a claim of his or her innocence. So this is what begins the trial process. Throughout the trial, the defendant is presumed innocent. The prosecutor's task is to present evidence to cause the rejection of the assumption of innocence, or a rejection of the claim made by the defendant. This is basically the same concept with hypothesis testing. We're going to be using a similar method in testing a claim. One party is going to claim that the population parameter is true, either mu or p, mu for the population mean and p for the population proportion. And this assumption is going to be held throughout the course of the hypothesis test. We are going to assume that the population parameter is true throughout the whole test, just the same way we assume the client or the defendant is innocent throughout the whole trial. And then the other party is going to say, look at the sample evidence. And by sample evidence, we mean X bar and P hat, sample means and sample proportions. A sample from this population will be taken, and the corresponding sample statistic will be calculated. So one party is going to say, look at the sample evidence. The jury is going to be us. We're going to determine if the sample results are sufficiently different for us to suspect that the claim is incorrect, or are close enough so that we can't disprove the claim. So, sample data is strong, the population parameter must be false, or we may come to the conclusion that sample data is weak, the population parameter is true. So if you consider the Gestamax example, the fact that the pregnancy length 268 was so far away from 266 on the bell curve, it was way off to the right, that is sufficiently different for us to suspect that the claim is incorrect. In other words, the fact that Gestamax produces pregnancy lengths that are longer than average is a correct statement. The initial suspicion is going to be that Gestamax does nothing to increase the length of a pregnancy. But by looking at the bell curve and recognizing how far to the right X bar was, it's sufficiently different from the mean, is enough to state that the initial claim that Gestamax did nothing for pregnancy lengths is incorrect. If the sample results in the population mean are close enough, meaning that X bar isn't too far away from the center of the bell curve, then it's not enough to disprove the claim. So we're going to be looking at sample data, and if it's strong, we'll be able to say that the population parameter is false. If it's weak, we have to say the population parameter is true. So let's look at this example, and I'm asking you to think about it critically and be the jury in this case. In a school district, the population mean test grade on fractions for all 5th graders is 72.4, and the population standard deviation is 4.3. So we have all the 5th graders in a school district. We have their test score mean, 72.4, and we have their population standard deviation, 4.3. A fourth grade teacher is using a new method to teach fractions he says is more effective. A sample of 35 fourth graders are taught fractions using this method. The sample mean test grade is 73.6. Is the teacher's new method really more effective? So, we want to know if 73.6 is sufficiently different from 72.4. If it's sufficiently different, then we say that the teacher has a more effective teaching method. If it's too close, then we say that the new method is no more effective than the old method. So, how do we decide if 72.4 and 73.6 are far enough away from each other? Well, to answer this question, to help us decide, let's answer this question. What is the probability that a sample of 35 students have a mean test grade of 73.6 or more? If we could find the probability of getting a result like this, but at random, getting a result of 73.6 or more at random, if we could find that probability, and if it happens to be a very, very small probability, then we may be able to say that the new method is effective. If it's not a small probability, if it's a likely event, then it's sufficiently close to, or it's pretty close to 72.4, and we're going to say that it really is no different. So to answer the question on probability, we have to first figure out the standard error, because this question involves a sampling distribution. We have a sample of 35 students and we have their sample mean. So to find the standard error, you're going to take 4.3 divided by the square root of 35. So 4.3 divided by the square root of 35, 0.7268. 0.7268. So after we have the standard error, we can use normal CDF to find the probability. Second, DISTR, normal CDF. Let's remember what the numbers were. 73.6 to 100,000. The mean is 72.4. And the standard error was what we just calculated, and I don't remember exactly what it is. Oh, I don't remember. 0.7268. So I'm going to just adjust this standard error right here to be 0.7268. I've got too many decimals. And then close the parentheses again and enter. Okay, 0.0494 when rounded to 4 decimal places. 0.0494. Okay, so this graphically is what we're looking for. We have the sample mean of 73.6 over here on the right. We have the population mean 72.4 in the center. Oh, that's a little incorrect. That should say 0.7. That should have the standard error. Okay, that should not say 0.43. That should say 0.7268. That's the standard error. So our probability, though, is 0.0494, and the way we interpret it is we say that assuming the population mean 72.4 is true, the probability that a sample of 35 students have a mean test grade of 73.6 or more is 0.0494. So the probability at random that we choose 35 students at random and their sample mean is 73.6 or more is about 4.94%, almost 5%. This piece of area, which is 0.0494, has a special name. It's called a p-value, a probability value. Probability values, or p-values, basically refer to pieces of area that are found going up to positive infinity, from an x-bar going up to positive infinity, or on the other side of the bell curve from negative infinity up to an x-bar. It's a piece of shaded area in the far right tail of a bell curve or the left tail of a bell curve. So extending up to positive infinity or extending down to negative infinity. It's just another word to represent the area, which is a probability. So let's remember that all 35 students received a different teaching method on fractions. Do you think the different teaching method is more effective than the current teaching method? So give it some thought. Do you think that our x-bar of 73.6, which has a likelihood of happening at random of 0.0494%, or 0.0494 and 4.94%, that's the likelihood of this happening at random. But every one of these students received this different teaching style. So, do we attribute this result to the new teaching style, or could it easily have happened at random? The more unlikely the result of our probability question, the stronger the sample evidence. So, before, with Gestimax, we had a likelihood of 0.62%. Here, with this teaching fractions question, we have a likelihood of 4.94%. The more unlikely event, the stronger the sample evidence, because the more unlikely something is, the further to the right of center that x-bar will be, because unlikely events have very small probabilities. So if we shift this x-bar up further, then the area to its right is even smaller, and the likelihood of it happening is even less. So, far away from center, if x-bar is far away from center, then we can say that the likelihood is very unlikely, but closer to center, it's not too unlikely. The question is now, how far away from center does it have to be to say that this new teaching fractions method is more effective? The smaller the p-value is, the stronger the evidence that the new method is more effective. So let's remember that p-value represents that piece of area, and the smaller that piece of area is, the stronger the sample evidence.